Hey guys, these are the notes for 3.8, regular polygon transformations. This is the last set of notes for Unit 3. On Monday we will begin Unit 4. So for this particular lesson, it's pretty short, sweet, straight to the point, or I will try to keep it that way. You'll be able to define polygon and regular polygon, describe a transformation that will map a regular polygon onto itself. And so let's get to it. When you're mapping a figure onto itself, that basically means that the image of the transformation exactly overlaps the pre-image. Or if you think about it as like folding something, like say if we look at this image right here, which we'll talk about in a second, if I were to fold this image over this line, it would literally land right on top of its other half. If I were to fold this image over this line, it would also literally lay on top of this half right here, okay? So only reflections or rotations can, they had the word could here. I didn't mean to erase map, just the could. Only reflections or rotations can map a figure onto itself. So no other transformation can do that. And the transformations are also known as symmetries of the figure, okay? Because symmetrical means, like for example, a line of symmetry is a line that just cuts a figure or shape in a perfect half, where if you were to, like I showed you in this case, take one side, flip it over the other, and it would lay perfectly. So it splits it into two exact images of each other, okay? So this half right here, let me roll that pen over, is the perfect image of this half right here, okay? And that's what symmetry is. And I did this butterfly that doesn't necessarily look like a butterfly, but the purpose was to demonstrate symmetry. All right, so symmetries of a figure. In this image, we're trying to describe all transformations that would map this rectangle onto itself. The unique thing about this point here is that it is the center point. So if you notice this point right here in the triangle, because this is a triangle, what's wrong with me? A rectangle, excuse me. This is a rectangle, 6 units here, 4 units here, 6 units here, 4 units here. Okay, so it's a rectangle. So this point right here is the perfect center point of the rectangle, meaning like from this point, it's 2 units away from this vertex, 2 units away from that one, 3 units away here from the left, 3 units from the right. Okay, so this is a center point. If you were to rotate around center point 2, 180 degrees, 2 turns, you would map this figure onto itself. Same thing if you reflected across the x is equal to 2 or the y is equal to 1 axis, or line of reflection, I shouldn't say axis. The x is equal to 2 line of reflection, or the y is equal to 1 line of reflection. Either one of these lines of reflection would map this figure onto itself. Important vocabulary. A polygon. A polygon is a closed figure, unlike this figure here or that figure there, right? Closed means it's literally closed. There's no openings. In a plane formed by connecting segment endpoints, and each endpoint intersects 2 other segments, okay? So let's put 2 other segments, that's important. All right, so for example, if you look at this example of a polygon, this endpoint here connects this segment. This endpoint connects this segment and that segment, okay? And then every other endpoint connects 2 segments. Same thing here in this octagon. Pick any segment, I'm gonna go with this one, and notice that it connects 2 other segments. This endpoint connects that segment. And so that's a unique feature of a polygon. A regular polygon is one where all the sides are congruent and all the interior angles are congruent. So I gave an example of a square. All sides are congruent, all interior angles are congruent, 90 degrees. An equilateral triangle, all sides are congruent, all interior angles are congruent, 60 degrees. And a pentagon, all sides are congruent. Excuse me. All sides are congruent, and all interior angles are congruent. Okay, and we're going to talk about what those angle measures are. That's a different lesson. The interior angles of a pentagon, hexagon, or any figure that's over 4 sides. We're going to talk about that separately so that I do not confuse you. Okay, so of course these are non-examples of regular polygons, all right? And so you want to make sure that you have all of that down. Now, go ahead, and this is where we get to the important stuff. Not that the rest of the stuff wasn't important, but this is a major takeaway. The rotational symmetry of a regular polygon, okay? So a regular polygon with this amount of sides can be mapped onto itself through a rotation of 360 degrees divided by the number of sides the polygon has, okay? So if you're being asked, what is the what degree of rotation would map this polygon onto itself? So say they give you like some like square or rectangle or some other polygon. You would take the number of sides, divide it into 360, and that would give you the minimum angle of rotation. Now, keep in mind, when we say minimum, that means at least. That is the smallest degree of rotation that would map a polygon onto itself. But any multiple of that angle will also map the figure onto itself, okay? And we're going to talk about that in the try it out. Do not worry about this section here. Skip over, and we're going to go straight to the try it out. So the try it out says, given the regular pentagon shown below, which of the following angles of rotation about center point O would not carry the figure onto itself? So what I did was I counted, of course, the number of sides in a pentagon, which is 5, divided that by 360. So when I divided that by 360, I got 72. I knew that 72 wouldn't be my answer because they asked which of the following would not carry it onto itself. Now, how did I know that 144 would not work? Because 144 is a multiple of 72. So any multiple of 72 would carry the figure onto itself, okay? So for example, 72 times 2 gives me 144. That means that 144 is a multiple of 72. Therefore, it would carry the figure onto itself, and the question is asking me which would not. Okay, 224 was my answer because 288, another way to do this is to divide by 72. And so if I divided 288 by 72 and I got a regular number, not a decimal, then it is a multiple. And in this case, yeah, 288 is a multiple because 72 times 4 would give me 288. All right, but what about 224? Yep, it gives me a decimal, and that's how I know that 224 is not a degree of rotation that would map this pentagon onto itself. All right, so you're going to go ahead and do the rest of the try it out by yourself, which is 2A, 2B, and 2C. Okay, have a good day. Bye-bye.